Welcome to module number 3, that is lecture first, and this lecture, basically this module is devoted to the control of HVDC link. First we will see what are the desired features for the HVDC link, then we will go for the control characteristic both for the rectifier as well as the inverter end, and we will see the various options and various faults, various voltage dip, etc., and then based on that we will derive the exact characteristic for the rectifier as well as your inverter end. Then later stage once we decide the exact characteristic for the rectifier and inverter, then we will go for the different type of controllers, how that they will work and they will give that performance at the later stage. So to see this desired features here, already I have mentioned several. Some of them are very common, that is required for any control aspect, any control schemes. For example, the control system should not be sensitive to the normal variation in the voltage and the frequency of the AC system. I mean that if there is some, if load is keep on changing, the frequency of the system will also change, and this change is due to the load generation balance. Whenever there is a mismatch between the generation and load, there will be change in the frequency, because the energy, whatever the difference is there, that is taken by the whatever the rotating mass in the system, it will be transferred, and thereby the frequency of the system will fall down or it will rise depending upon the mismatch. Means if your generation is more than load simply, then frequency will rise. If your generation is less than your demand, frequency will fall. So normally this frequency variation is not much, but still in our system it is plus minus, sometimes goes up to 3%, but in other countries normally they maintain at very nominal 50 Hertz rated value. So it should not be very sensitive, because if your frequency is changing, your controller keep on changing from one mode to another mode here and there, then means your controller there become controller unstable, means controller instability may occur, that we don't want. Also the voltage variation, if the small voltage is varying here, the small fluctuations you can say, sinusoidal is there, but there are some variation, it should not be much sensitive to that one. No doubt, if the voltage is varying huge, controller must take care so that it should do its desired objective. Second feature is very similar for any controller. We want that our controller should be fast, it should be reliable, and it should be easy to implement. We can devise a very complex controller, and that time that controller is not useful, because the implementation itself is a very difficult task. So it should be simple as well, so that we can easily implement, and also it should be reliable, means we should rely on that, means there should not be any failure, otherwise huge power blockage from one end to another end will occur. It should be fast, even though sometimes we don't want very fast action in several aspects. For example, if a relay is there in AC circuit, we want that relay should not be very fast. It should be fast, but not very fast. I mean, if there is a small variation somewhere, suppose current spike is there, and if relay is operating, means it will trip the circuit. So we don't want. But here we want the fast operation, because there will be any fault in the DC link, the huge current will flow, because only there is no inductance, only resistance is there, huge voltage is there, and there is a short circuit, huge current will flow, and that may damage the line. So HVDC control, we require the very fast controller as well. And we'll see, even though if you are controlling your power electronics device like your converter, you are firing here, you can control very fast, but there is an option that you have to go for the, even though sometimes using OLTC, that is online on load type changers. If you are doing that, that is a mechanical device and that will take time. But first we go for the firing of the arresters, and based on that we can do our objective of the control. Third objective is related to the continuous operation range from the full inversion, full rectification to inversion, or vice versa. What happens normally if you are having a big HVDC link for the bulk power transfer, always the direction of power is unidirectional. Means if you are transferring, huge generator is here and you are providing the power over the bulk HVDC line, and there is a load center, always it is unidirectional. But as I said, we are having the different type of schemes for HVDC links. It may be your back-to-back connection, where the power from one region is flowing to another region, and there is a possibility in sometimes it can go back. So once your rectifier, which is a converter working at the sending end power, is working as a rectifier, there is a possibility that power reversal is there in that line, and this is the advantage of HVDC. Means it is not only controlling the power, it can reverse the power in the different direction. So whatever the rectifier operation is there, it should also sometimes require to act as an inverter. So that is why here, and it should be continuous, it should not abrupt change. So if you are operating from the rectifier, you can go to inverter and then again inverter to rectifier whenever it is required. So this is called, it should have a continuous operating range, it should not be different here and there. Another, the control your scheme here, we are talking here, the control means control of HVDC, the control scheme, which should require the minimum reactive power support. As I said, you know, normally it requires the 60% reactive power due to the delay angle. If your delay angle alpha is delaying, the power factor is going to be worsened. So we require the reactive power control. Here we will see, you know, this DC power in the link, it is nothing but your VD into your ID if we are talking at the rectifier end. If you are ignoring the losses in the line, the VD at the both is almost same. So this control here, that we will see here, we are trying to maintain fixed, and this we are changing by the rectifier operation, and due to this change, what happens, this VD will be controlled by the delaying your angle, means your delay angle, means if it is you are operating rectifier, so you have to change your alpha degree, and if you are operating in inverter, then you have to delay, you have to change your beta. So once you are doing this, then the reactive power requirement is going to change, and therefore you require huge reactive power support at the both the rectifier as well as the inverter end. It is always, if I can just draw a HVDC link here, I can say simple 6 pulse link here, the 3 phase is there, and this is your DC link. I can say it is your any link you can assume. Here it is a 3 phase. This is HVDC rectifier if the power is flowing from this end to this one. If power flow is this is your PD which is flowing from here. Now one thing is very, here you can see the power here, the reversal is, if you are doing this is a negative operation, if the voltage is the reverse, current direction is same, then power is reversed. The option that you can reverse this current and change the voltage, that is also option, but what we do, we prefer that the current in this link should flow in the same direction, it should not change. We try to change the voltage here, this VD, to change the power. So if VD is 0, PD is 0, but if you want to reverse the power, here simply you change this, means this will operate in rectifier, this will operate in the, this will operate as inverter, this will operate as rectifier, then the power flow will be this direction, but the direction of current is still maintaining the same direction. So it is a unidirectional current always flow, whatever they design. So normally we talk if power is flowing from this end to this end, as I said, if you are having huge generation this side and this is your load side, then what happens, always the power is flowing from this end to this end. But nowadays we are going to use for the bulk back to back connections, means the two regions are connected and not very high power is flowing, and it is basically based on the need of the different region. So power can flow from this end to this end, this end to this end. So in this case, I want to tell this one, the power is here, now AC power here I am talking, this AC, here you will also require the Q at this converter, if it is a rectifier. Here it is inverter, your PAC is this one, but your QA is coming here. Means it still consumes reactive power from the system, AC system. This is basically this side we are talking the transformer, this is the AC bus, here this is AC bus. So the reactive power basically required both end, and we put, now you know, and already I discussed about the filters. Once we will go for the design of the filter, we will see we are going to use some of the filter to harmonic to eliminate or to mitigate the harmonics that should not enter this side, means we provide the minimum impedance to ground, and that at the fundamental component it provides the reactive power, means that will work as a capacitor, I can say simply effective capacitor, although it is made of inductor and the capacitor together, so that we can have either tuned filters or maybe band pass filters. We will see the detailed filter design later on. So that even the filters provide some of the reactive power, but still we require some reactive power from the source. To minimize this reactive power, here the firing angle or here the firing angle can be constrained up to certain limit. Normally what we do, your alpha here, normally it is 10 to 20 degrees. We should never go beyond the 20 or 30 degree, because if you are going for more, your requirement of reactive power becomes very excessive. Similarly this size also. So that's why here we should have a control scheme in such a way that we can operate here even though in this range itself, not beyond this. So if you are operating less than that, your reactive power requirement will be less, and that is saying this feature. Here another, this is said, this feature says that under steady state condition the valve must be fired symmetrically. We are talking about all the valves, that we are giving pulses at every 60 degree. So why it is so? If you are not firing, you may design a controller that may give even the same value, but your symmetricity is not maintained, means your output is not symmetrical and you are generating so many harmonics. So here, due to this symmetrically fired valves, we are minimizing some of the harmonics. And you will see later on, if you are not symmetrically here firing, what will happen? You are not only getting this harmonic, that is the NP plus minus 1 in the AC side. This is a components that you are getting, number of pulse here, here n is any integer. So for 6 pulse you can say you are getting 5, 7, then you are getting 11, 13 or so on. It is only valid if you are having this symmetrically fired valve. If you are not doing this, then you are having all the harmonics component and interharmonics components that will be going to your AC system. So this is also required, that we should fire our valve symmetrically. Now the question arises sometimes that even though you are giving symmetrical pulses to the valve and one is misfired, or even though there is a commutation is taking place and commutation failed, then in that case also we are not changing our philosophy. Pulses are getting every 60 degree, so that we will see after one cycle this whatever this misfire or commutation failure is disappeared in the system. No doubt during that cycle there will be, your voltage will be not symmetrical and you are injecting more harmonics, but next cycle it will be automatically cleared. So main concern here, to minimize the harmonics, we have to give the pulses symmetrically to all the valves. Now some more features here, for example, that the control should be such that it must control the maximum current in the link and limit the fluctuation of current. Here this control says that here, because suppose if current is excessing flowing in your link, in this link the current can vary. If you are varying here, what happens? This controller may oscillate. So we want that this current should be steady state, this fixed value, and also in the emergency condition, some of the times, let's suppose voltage has gone down, there is some fault this side, this current should not exceed. So it should have some maximum limit, beyond that it should not go there, and controller should decide that it should take care of that. For example, even though you can say if there is a fault here, what happens? This current will exceed excessively because only very small resistance of the line is there. So huge voltage here, because there is no reactance, no circuit breaker, this line will burst. So we can maintain anyhow that this limit during any abnormal condition I am talking, it should not increase its maximum value, it should have certain link, means normally it is not more than twice of this rated current for fraction of minutes, it is not even the for steady state. Now another is the power should be controlled independently and smoothly, which can be done by the controlling the current and or the voltage simultaneously in the link. As I said here, to control the power, as I said, it is possible that we can control this, we can control this as well together. Here, as I am saying, the simultaneously means you should control only one at a time. It's not that both. You can control this, then you can change this. So it is always better to have one control and then take this one. Means to control this here, it is better either you control this or you control this to control this, not both voltage and current, because then your controller becomes very complex and that time may give some unstable solution sometimes. So in this one, what happens, we only go for the voltage and we try to maintain the current in the system constant. Another feature we require, because limitation of DC circuit breakers. So far, even though now people are doing a lot of research in the DC circuit breakers as well, but still in the commercial way, on very bulk rating of the current is not available. So what happens if there is any fault, we cannot open this line at once. We have one option here to control this. We can reduce this voltage, automatically current is 0. So we require that we should operate in a such a way, your controller should be such that it can even protect this your converter circuit as well. Because in AC circuit, what happens here, the circuit breaker is there, you have AC circuit here, this is line, here the circuit breakers. If there is any fault here in the line, this will be basically, it is open here from this side because we have the AC circuit breakers. Here we don't have any option. So we can use a controller for this and this. We know that we have some option here to control very fast, because we have the firing angle, they can be fired very quickly, and then we can simply try to reduce this voltage 0, fault current will be automatically 0. Means that is just like an open circuit. So that's why here this feature say that our control scheme should be also such that we can protect the system as well with the help of controllers, not with the help of circuit breakers. Now, as I said, we are operating here the constant current mode and changing the voltage. Now there is two options. We can operate at the constant voltage mode, means this possible, it was possible that this is fixed, we can change this. It is also possible to control the power. Only one quantity is required to, because here to control the power, the current you can change, and the current direction if you are reversing, then still the power is changed, the reversal is possible. So here we prefer in this control HVDC link that this current is constant but voltage is varying. Now then always there is a question why it is so. So that's why here I am going to analyze the two options. If you are operating at the constant voltage mode or constant current mode operation, how it is going to vary and differ in the technical detail. So we just see here I am writing the voltage constant and another is your current. Let us analyze current constant here, and we can see what are the various options are there. You know, normally in the AC circuits, always voltage is fixed because all your operators are operating almost same voltage. So what happens in the voltage constant mode, you have to connect your loads in the parallel of the loads or supply system. Means for example, this is your one load, this is your V. If you are having any load, you have to connect the parallel to this. So what happens, the voltage is fixed, but the current drawn here flowing is the different. So all the loads are basically connected in the parallel in this scheme. Here the constant current, what we do, we connect all this here, the loads in series, so that whatever the current is flowing here, here is the same throughout this value. Here the current is different, here the current is different, because this depends upon what is the impedance of this load. Means what is, you can say, value of this load, impedance here as well. So the current here is varying, voltage across all these things are same. So all the loads are bearing same voltage, different current. Here all the loads are having same current and the different voltages, because here the Z1 here, Z2 and Z3 are the different for the different loads. So this is your constant current modes of operation. Now this is the first characteristic. Second characteristic, let us see about the, if you want to replace any of the load, if you want to replace this, simply you can take it out without any delay, without any problem. But here you cannot take it out. If you are taking it out here, what happens? The current is 0. So what we do in this mode, we normally bypass it and then we take it out. So it is not easy task. First you have to bypass with the somewhere and then you have to take out this load, or simply bypassing means itself it is out. But you have to open here, no doubt, if the voltage is there. So here you can see the bypassing, here the simply taking out. This scheme is still, I can say it is a complex to remove the load in the series circuit. Now second, as I said, see about the losses. You know this losses here, that is a loss, it is here I am talking about the loss in the line, because loss always occurs in the lines, not in the load. Load itself is a loss because the energy is dissipated. So we are talking here, there is R, let us suppose. So this current which is flowing here I, so it is your I square or whatever this is, let us suppose this RL is the resistance of the line. Here if you are having the resistance RL, here also the loss will be your I square RL. Now see, this I is the different, then this I, we are talking both I is different. This is for the constant voltage mode, this is a constant current mode operation. Now you can see here the loss, this loss is constant irrespective of your load, irrespective of your voltage here, irrespective of the voltage across the load. Loss is constant because current is constant. See here, this current is keep on changing, that depends upon the loads. If one load is there, current will be less. If you are using another load, current is again further increased, and so on and so forth. So this I is keep on changing depending upon the minimum loads to the maximum load. So from here we can see the loss here is less real power loss compared to here, which is fixed and constant throughout the operation. Now third option we will see, there is another loss that is called corona loss. Corona loss, this loss is proportional to your V square. This loss is proportional to V square. Now the V of this line is fixed, so this loss is constant here, but here we are, the voltage is changing, so your corona loss is changing. Although corona loss is not very high, but if you are going for the EHV transmission system, then this loss is significant, because here this loss is going to be less, means I can say corona loss, it is also here proportional to V square, and it is keep on changing. Now you see another difference here, this RL is more than this RL. The AC resistance, if the same wire you are using, AC resistance is more than your DC resistance due to the skin effect. So if this is 1 ohm, it may be 1.2 ohm. So this value is still, now the loss is also slightly higher, but it is varying here. Here this loss is varying, and also this loss is less in the DC line compared to your AC line. As I said, this corona loss is proportional to F plus 25, that is the frequency. So here the frequency is 0, so this loss is less, and also here the voltage is varying, so this loss is extremely less. Even though you are operating at the, as I said, the bipolar operation, that is a plus minus 500 kV, means you are operating the two lines, line to line voltage is 1000 kilovolt. So in that case this loss is very significant, and it is going to vary, means it is less sometimes depending on the power control. So the total, you will see the losses is not much difference, either you are operating this or you are operating this. But in the most of the practical cases, this loss is less than this loss. If you are operating at the lower voltage, this loss is almost 0, because we require some voltage, that is the V critical voltage. This voltage is minus certain this ionization voltage, V minus VOC. So if it is less than, suppose you are operating it's 400 volt, this is 0, corona loss is it's totally 0. So it again, that's why here we are going for HVDC, high voltage. In high voltage these losses are significant, corona loss as well. Now fourth is, that is a very important, and this fourth is nothing but related to your fault current. Means why we are operating here the constant current, that is related to your constant current here, and I can say your fourth option. You see, if there is any fault in the system here, what happens, you have the circuit breaker, and you have, even though not only resistance, you have the reactance of the line as well, and therefore here your the voltage divided by your this R, whatever you can say, this line plus your fault resistance plus your, you can say, Jx, whatever, this is the current which is coming. This is normally it is a 5 to 6 times depending upon what is RF value, etc. But what happens, you have the circuit breaker, it will be automatically tripped. But if you are up here in the constant current mode, your current cannot exceed that value, current is rated current. So even though there is a fault, the current here will be the ID here. But suppose we are not operating with the constant here ID, what happens, you are operating here as a constant voltage and the varying current. Now you can see if the fault has occurred here, this voltage is constant and this resistance is very small, as a DC resistance, no reactance, DC, and that value you are divided by your RL is, this current is almost 20, maybe 20-30 times of the rated current, and then you can imagine what will happen to the line. So if you are operating here as a constant voltage, varying current, here because even though you are using any circuit breaker, any scheme, but still this is a 20-30 times current is very high. And these basically the regions here we found that here is not a much difference in the loss for EHV lines, for high voltage lines. If you combine together, you will find the loss is not much different, but this impact factor is very high because we want that here there is no circuit breaker, and also only is the limited, the fault current is limited by the fault resistance as well as the resistance of the line. So if you are operating at the constant current mode, no doubt there is a sudden jerk is there, but your controller will act and finally the current will be again maintain the same value. So normally here in this case the current, if you are here, can go several times, here it can go twice of the rated current. So this feature basically advises that we should operate our HVDC link in the constant current mode and the varying voltage to control the power over the line. So now I hope it is justified why we are using the constant current rather than constant voltage, which is practiced in the AC system. Here it is a practiced in the DC system. Now come back to our equivalent converter circuit along with the line. If you will see here, I already derived, this is your rectifier, that is you can say cos here, the VDO R here I have written the cos alpha, and it has your commutation resistance of R denotes your rectifier and I this side denotes your inverter, and this is your VDOI cos beta RCI, and this is your resistance of the line, that is RL. Here this ID is flowing. Here we are having the transformer. This is the equivalent single phase of this whole circuit. Here we have taken the single phase here this side. That AC system, if it is balanced, you can take a single phase. So this is a complete your equivalent model of rectifier, line and the inverter. Now you can only from this circuit we can write the what will be the ID in this link, and that expression here I have written simply this voltage minus this voltage divided by the resistance of line, commutation here of the rectifier, and here the inverter commutation resistance. Now you can see this expression is written. Here if you are using beta, if you remember, it was the equation was the plus, so here it is a plus RCI we are using. If you are using gamma, then it was the RCI was negative and we are using here the minus 1. So the bracket quantity if you are using, then it is a minus. If you are using beta, then it is a positive resistance. Simply remember we derived the expression for this one. Here your VDI was your VDO I, here cos beta plus here your RCI ID, if you remember this, because you can see this current is flowing this side. So, this voltage plus this voltage or this voltage. So, this was plus, and if you are using here the VDO I cos gamma minus RCI ID, if you are using this, from here you can just derive it, and already we have proved it. So, now this is equation for the current, and based on this equation we will analyze the what should be the characteristic of our controller for both rectifier as well as the inverter end. Now, as you see this end we can either operate at the beta mode or gamma mode. It is possible. Either you can decide your beta instant or you can maintain the gamma based on your. What is the gamma and beta? It is as I explained here in the inverter operation. This is your commutation voltage. Here this is from this side, if you are going, it is the 0 here, and you are firing, this is your alpha from here to here, and if you are firing at here, this is your beta, that is a, and we are measuring from this end, means this beta value is pi minus alpha. So, this is your beta where you are talking, then there is a u period, and then this is your u period, and this is your gamma period. So, either you are denoting again this gamma also measured from this end and beta is also measured from this end, because the beta is nothing but pi minus alpha. So, this is your alpha now. So, this angle is pi minus alpha, this one. So, this is your beta degree. So, either we can operate our inverter by here knowing this value or this value, but it is always preferred to use our inverter end with the gamma control. The reason is, here as I said, if you are not maintaining this minimum gamma, there is a possibility that this will be going when the voltage is reversed, means commutation between the two valves are taking place and the voltage may reverse without completing the commutation. So, it is always desirable to maintain some angle here, maybe 10 degree here or 5 to 10 degree, so that there should not be any commutation failure. We will see the commutation failure when we will talk about the mal operation of converter circuit. So, it is that is why here it is written for maintaining the safe commutation margin, gamma is used as a control variable instead of beta, because once you are using this beta, what happens, then there is a possibility you will change and you cannot maintain the gamma at that time and you may face the commutation failure. But if you are maintaining this, based on that you can compute what will be your firing angle, because you have to give the firing pulse to this your valves. So, this is required, but what we are doing, we are trying to maintain this. Based on that we are calculating the instant, we will see how this gamma control is done, how this beta is calculated. It is calculated, controller will calculate, and then it will give the firing pulse and then it will be done. So, even though while calculating, what happens, there is a possibility there is change in the AC system. So, you may change. So, that is why we are maintaining here 10 degree, even though there is some change also it will take care. So, instead of beta we use this gamma control, and this is basically we will see it is called the constant extension angle control, and this angle is maintained minimum value constant, and then thereby we control other things. Only problem here in this controller, that due to this negative resistance, you see now this is a negative resistance. Here you can see in this expression, if you are using gamma, we are getting here the negative resistance. It is not a resistance, it is basically effectively due to the inverter operation, and this resistance, negative resistance is very difficult to operate that controller stably. So, it is very carefully, normally this type of controller, it is not we change too much, so that there should not be any stability problem of the controller at all. This negative will normally, if you are working on the negative resistance, it is always possible that operation may not be very smooth. So, what we do here, we try to maintain this gamma. We will see these factors will be taken care while deciding the characteristic. Means what we are doing, we are not changing the gamma here, the gamma is fixed now, that is 10 degree, and then you do whatever you want. So, this side only we are trying to maintain the gamma only. and we will see whenever some emergency occurs, it will go in the different mode also, and then when we derive all the characteristic, then it will be clear to you.
Actually, in DC constant current we are maintaining, and we are connecting all the loads in series.
Yeah.
So then the load should be designed for constant current. They should not be different current.
Yeah. What happens this type of schemes, even though there is no DC loads nowadays, means DC load, I mean that all the loads are fed with the AC system. Here just I was comparing that if it was possible. In the beginning days when we were having the DC supply only, they were connected like this. So at that time the voltage rating, of course it is changing, voltage across each equipment is changing, but you can also see here, if you are, let's suppose this is your instrument, the current is constant here, so constant current right now, but this impedance is known to you. So the voltage is also fixed here. So the voltage is also here, you can know how much voltage is appearing because current is constant here, because the impedance is basically we measure whether it is even the motor load or whether it is your lighting load itself. So this is fixed, this is now voltage you can calculate based on the jet. So you can say this voltage or this current, almost same thing.
More than one load.
If more than a load here, what happens? This voltage, now you can say the voltage is shared, but not this voltage is here, we are changing the voltage here. So this voltage is still same, it's not going to change. Across this voltage, what was, even though it is not connected, the voltage again it is going to be same, because the current, this jet is a different, here I is same and the voltage is this one. So either you are connecting this load or you are connecting this load or you are connecting both loads. The voltage you can see and current is not going to change across the instrument.
But sir, while in the fault, we have to change the voltage for maintaining the constant current. The current voltage is being changed of the source. How is the constant current operation means?
No, basically now the question here, if you are having some way to control, either we having converters, you can control the voltage. This is not practiced in the AC system, first thing. It is practiced in the DC system, and in early days normally people were using this. When only the DC and small loads were there, it was not bulky. But in AC always it is preferred, again compared with the AC, here the constant voltage and constant current here, and we found here this is this system, AC system, where the constant voltage is better than the series one. So this was used in the beginning when the very small loads and very DC generators were there, but now it is not so. Now we are, even the DC generators also feeding the same type of parallel loads we are connecting. Especially for small voltage loads, the constant voltage scheme is more efficient. But if you are operating here in your, this is a constant current for high voltage, I said the two regions losses are not very much more or less similar. No doubt this is a constant voltage loss may give less, but the another thing I said, the fault current, that is very important, and based on that we operate HVDC links on the constant current mode.
Regarding that, I have a question that we don't have actually the current source. What we have the voltage sources.
No, even though you are having, let's suppose a DC generator you are having.
And DC generator will means have a constant current or constant voltage?
Listen, here the DC generator, whatever the DC generator you are having, is a series or shunt or separately excited. The voltage you can change, and how the voltage change, this you can change the field, and field can change, you can measure this current, you can, what is your measure current, what is your reference current, this can change, you can maintain the voltage across the vary.
To maintain the current, constant current,
yeah.
We change the field.
Field here, yeah.
We maintain the field.
Yeah.
So in the case of fault,
yeah.
In
Here.
the case of fault, the current will suddenly go up.
No, here the controller is there. If the fault will rise, again it will try to reduce the flux so that voltage will reduce.
So similar controller was there in the case of constant voltage case also.
No, in that case voltage always fixed, voltage is not changed.
Yes, sir,
here you are using the AC system where the voltage is fixed, it is not changed at all.
A controller is maintaining the constant current in the line.
No,
and when the
listen, what you are talking about now, it is right now AC system, or you are talking about this controller, both are separate things.
I am talking about that a controller is used to maintain the constant current.
Where? Now where?
In this system.
This system is a DC system when early were there, now we don't have this system. So So in that case here, if only you said we cannot have the variable voltage. Earlier there was no power electronics device, people were using the DC generators. In this scheme, it is possible that you can change the voltage and by the here maintaining the current.
I was talking about you have proved that because of the fault current, we
Yeah.
use constant current system.
Yeah.
So I was saying that to maintain the fault current constant, there must be a controller at the generator side.
No, we will come to this controller, how it is decided. I didn't discuss about this. I said we require the constant maintained current, and now we will decide what will be the characteristic of this side and this side. We will see this. I am going to derive that characteristic. Still I didn't come on the characteristic. And for your knowledge, we will see here this rectifier, basically we are going to have this characteristic. Is one zone. Here we will find this is going to be like this. Here this is going like this. And I will come each and every, now here again I will change it here. Now it will be this. Again I will change later on one by one here, and we are going to have this characteristic. So I will give a region for each why I am changing this. So still it is, you are in the before. So we will see how this characteristic is going to change. You will see here the constant current characteristic. Here there is also constant characteristic. Sometimes it will be hitting limit, it will shift here and there. We will just discuss here. So my intention was here not to explain much, because I explained that if you are operating the constant voltage or constant current, how much you are going to get, means what is your efficiency of the system, and why we are using the constant current in the DC system. Because the main reason we don't have circuit breaker. Only our converter should act, and that's why we require the controller that will work as just like a fault protection of your system. So we'll see, and now let us see, and we have to derive one by one the characteristic. So as here already I have written, which I discussed to you, that to control the power in the two terminal DC link, it is desirable to have current controller in one converter and the voltage current in the second controller. Why we want the control should be the different in the different, because it is not that every time it is switching here and there. We want that one controller should take the current, maintaining the current, and another should control the voltage, so that we can control the power smoothly. So because I said we require the fixed current, this is fixed. So one has to take care, either this side or this side, and we will see from this equation it is required. And another side, we require the voltage control. Now the question is that which will do this, which will control your voltage. The option is there. We will see where we have to go for the constant current controller. This means maintaining DC current constant, means we will have the constant current control, and it is always CC. We also want that this VT, our inverter end, as I said, due to the commutation failure, will come, I will derive, and we will see that we want the constant extinction angle control, and it is called CEA control. We will also find another characteristic is required, that is we will see the constant beta control, as well, and we will see constant alpha minimum control, it is also called, and it is called the constant ignition angle control, CIA. We will see all the controllers why they are required once we will analyze whole system as well. Now to see how this current is maintained the constant. Now from this equation you can see here already I have written, to increase the power in the link can be achieved by reducing alpha, which also improve the power factor, and increasing the beta or gamma, which will worsen the power factor and the higher loss in the valve. Now you can see from here, means this is a constant. Now we want to control the VD here. This is your VD basically. We are maintaining the current also, and this is the VD which is varying. if you are varying here alpha too much for voltage, what happens? Suppose you are varying from 0 to full value, this alpha becomes 90 degree. Approximately, it is again overlap and other things you are just taking care, so that is a different issue. But this, if you are going to deteriorate much, you are reducing alpha, means you are increasing alpha higher, what will happen? The power factor is going to be very worse, very poor. So whatever the power you require, maybe the more reactive power you require at that time. So what we do, we try to maintain this some value should not go beyond the 20 or 25 degree. So then this side we have to come, or we have to use this one. This, how you can control this? Because we are having the tap changer. So first we have to go for this because it is very fast. If it is exhausting its limits, means let's suppose it is reaching 25 degree, then we have to switch. We have to try to control here the voltage by this. Let's suppose this is still exhausted, then we can come this side, because this we want to maintain constant, because we don't want to change it here. We can even though go far here, for example this is the minimum value, but we can also increase this value. Again, if you are increasing this, your power factor going to be worse, inverter end. So you can even though reduce this, but it has some limiting value and it should not come. And this then option is your inverter end. Now let us see some of the impact. So based on that, as I said, here it is required to operate inverter as the minimum gamma, means let us draw the characteristic of the controller. Here it is your voltage, here it is your ID, because we want to the characteristic of your whole circuit based on the voltage and current. So it is, we require that this should be there and it should not, this minimum should not be reduced. So what happens, the characteristic you will see, it is the gamma minimum here. Why? The equation I wrote the voltage equation. This is your VD here, this inverter end, it was your VDO I cos gamma minus RC ID. So this is the slope of RC ID. So this is a slope here, and you can find this is the characteristic, this is called CEA, and this is your inverter end. Means it should not, it should have a certain limiting value. It can reduce the alpha can be larger, but not less than this value. Now then, if it is in this one, then we require another option that this should be control constant. So this option, to maintain the constant, we assign rectifier should take care of this, because this end now we are fixing this. So what happens, your rectifier here, it is your constant current control, and this is your ID value of the rated, and this is called the CC or constant control, that is the rectifier is doing. And your intersection here is your actual operation of your DC link. Always this controller and this controller, the characteristic will match, and then it will be your actual value of operation, because this ID is governed by here, this equation voltage, and then constant controller here. Now let us see if there is some change, and that's why I will go for the characteristic change later on. Already these things I said, that here rectifier operates at the constant current control, and the inverter is operating at the CEA mode, that is the constant extinction angle control. And also I here mentioned about, due to the negative resistance, the stable operation, we just keep on changing gamma here, there may be problems. So normally this is a fixed value here. Now let us see the AC side voltage impact. If there is a fault in the AC side and here and there, how it is going to vary. Now first I will take this case when the rectifier AC voltage is increasing. Rectifier AC voltage increase means this increase, because this is having the rectifier AC side voltage, that is EM. So if that voltage is changing, means this value will change. I am saying, if let's suppose voltage is increased, what will happen? If this voltage is increased, this current will also increase. Means here, due to the first option, this your rectifier and this AC voltage increases, then your VDO R will increase and this will cause your ID will increase. It's obvious this will increase. We are not doing anything here and this is divided by this, it will increase. So what will happen? Your rectifier, which is trying to maintain the current, it will try to change this alpha and it will try to increase the alpha so that this should be reduced, so that the multiplication here should again maintain and the current should be maintained here. So what it will do, it will be going for cos alpha, here it will be reduced, means alpha is increased, and this will be nothing but what will happen to your system, the power factor will be poor. So what we have to do, we have to delay this angle alpha further, but we have to stop somewhere so that the power factor, because we have the reactive power limitation, so it is alpha should hit its maximum value, maybe 25 or 20 degree, and then we have to stop it. The controller will not. Then still, let's suppose the current is not your rated value. What will happen? Then our OLTC will come into picture that side, and here our this now OLTC of rectifier will be exercised then and to maintain this one. Now the question still arises that if still it is not maintained, we exercise this first, then we exercise this first. Possibility may be if huge drop, means AC increase, then what will happen? Still it is higher. Now we have to increase this side this. We cannot reduce this because it is already constant extension angle control mode. So here we have to do this, means your AC voltage OLTC here has to be changed. No other option, and this will be taken care. Now the question you can say, if it is still not maintained, because the voltage increase cannot be more than 5 to 10%. If it is happening, your line will be burst first, AC system, because voltage is AC voltage, let's suppose it is 400 kV, voltage cannot be more than 420 volt, because there is other AC system is there that will be over voltage and everything will be tripped. So that will be, even though from here only itself you can adjust this voltage. So now you can see this. Now the same scenario, if this voltage is reduced, second, this rectifier and voltage is reduced. If this voltage is reduced, what will happen? Your VDO R will be reduced, it will go down. Then what will your rectifier will do? It will be your ID will be also reduced, and this will be trying your cos alpha should be increased. Okay. If the cos alpha is increased, means we are alpha is reduced and we have to set alpha minimum here. Means it cannot be reduced at a certain value, because normally we maintain 5 degree alpha minimum, so that all series valves must be fired in that degree, that time. So this alpha minimum is there, it will hit this limit and still it is not maintained, then again OLTC will take care. And still it is not done, then this will be taken care here. So now you can see from there we are having this characteristic here, means we are somewhere, it is your value is here and it is your alpha minimum characteristic it is hitting. Means it is not possible here to maintain this, means because this is the alpha minimum is hit, now this will be stopped, that's it. It will be, maybe your OLTC will take care, suppose it is not taking care, then we will see another will take care. So this is here, alpha minimum characteristic is also given here because it cannot go here. So that's why here is a CEA, here CC, here it is also called CIA, that is a constant ignition angle control. So with this I can stop here, and we will see other effects in the next lecture, that if this side the voltage is changing, increasing and decreasing, how this controller is going to act, and thereby we will just change this characteristic and we will see that is basically required. So So with this, I'll stop it here, and we'll meet in the next lecture, and we'll see how this control complete characteristic, both rectifier and inverter, is done. Thank you.